Good morning, everyone. Come on in.
Good morning.
Anybody have any questions before we get started today?
Your camera's really slow today,
Okay.
Professor.
Let's try something else. Hold on. Let's see if that improves it a little bit. I've been getting mixed reviews regarding whether my Ethernet cable is working, so still trying with it and without it. You'll notice I did put the lab up for this week, and it is sequence 1 lab 10 PHET Springs. So I've already got that up, and I actually put it up yesterday. Anybody have any questions on anything before we get started?
I don't see it up there, Professor.
Let me double check. Maybe I did the wrong class or did. Oh, yep. Last night I must have clicked it off again. Now you should be able to back out of the course page and then back in, and you should see week 11, which is actually supposed to be week 12 for some other reason. Evidently, I guess I didn't change that.
I see it now.
All right, I'm changing it to 12 right now. Oh, crackhead. November 8 to November 14. Now we're in like Flynn, whatever that means. All right, so everybody sees it now, hopefully. So this lab is in actuality sort of the capstone. It's not at the end of the course, which is, a little bit different for a capstone assignment. But what we mean by that is our very first labs was just getting you used to the numbers and how to deal with numbers and how to represent a result as being good or bad, with percent error, percent difference, sig figs, and of course I introduced the propagation of error formulas as well. And then we showed you just some fundamental ideas about how graphing software like Logger Pro and how ultrasonic sensors can detect distances, and then we could make some sense out of velocity versus time graphs, acceleration versus time graphs, and position versus time graphs. So that was sort of getting you the concepts of graphs, whereas the first couple were just getting you the concepts of what's necessary for lab. And then from here on out, we've been doing stuff like linear graphing 2, nonlinear graphing 2, and those were all about ways to analyze data. Okay, in other words, when you're faced with some physical phenomenon and you find out that 2 particular variables are interesting or helpful to you. So for instance, like if you're talking about a pendulum, maybe you're interested in more than 2. It might be the period, the time it requires to swing down, back up, and back up to the original spot. That's a time period that might be interesting to you. The length of the pendulum might be interesting to you, and you might even wonder how it relates to mass. You might even wonder how it relates to gravitational acceleration. Is it going to be the same on planet Earth as it is on, say, Mars or something? So those are some of the variables you could come up with. Then the scientific method would say, okay, well, why don't you go and figure out how those things, and I say the scientific method, there's not really one scientific method, but the process of science would say, go figure out how those are related. And often that starts with a hypothesis. Maybe you think it's going to be period and the length of the pendulum are directly related, because heck, after all, the length of the pendulum is directly related to how far it's got to go. So if it's got to go a far distance, it should be a large time, so on and so forth. But you also realize, well, wait a second, that length also relates to how high it goes, and that's how fast it goes. So maybe it's not exactly related to that. But that's all in the reasoning component, not necessarily in the experimental component. So what you do is you decide what variable is going to be independent. And in this case, we'd probably say period. And what variable is going to be dependent. So we might take, ideally, you'd want to take one variable at a time and keep all the other ones constant. So for instance, you think mass, you think length, and you think gravitational acceleration are all related to the period. If you're going to do that, maybe you even think how high you lift it is relevant as well. So that's another variable. So what you would do is say, okay, well, I'm going to test, I don't know, length. Okay. Well, if that's the case, then you should bring all of them with the same G. You should have all of them with the same mass. You should all have all of them pulled up the same amount, which you could measure by an angle, say. So by eliminating all those other variables changing, you can see just the effect that L has on T. And then what you do is you try a bunch of L values with the same M, the same G, the same theta, which is the angle that you pull the pendulum out from to start it. And then you plot period versus length. And then we learned through these 4 labs, linear graphing 2, nonlinear graphing 2, that you can graph T to various powers or L to various powers or T and L both to various powers until you get a straight line. And then once you have a straight line, you have T to whatever power you graphed it is equal to M times L to whatever power you graphed it plus B, because that's the equation for a straight line. And by doing that, you can slowly figure out how these other variables related. So you've now got the relationship between L. Now if you actually know the L, you don't necessarily have to keep the L constant, but it would be better if you could. So now you can keep the L constant and try different masses. And then you can keep the L and the mass constant and try different angles. And then you could, keep the mass, the length, and the angle constant and try it under different gravitational acceleration, which would require you to go to the moon or something weird like that. Or you could actually do it while accelerating upward in an elevator. But you have to find an elevator that can accelerate upward for long enough to run like 10 periods of a pendulum. So it's a bit tough, but that is a brute force way of experimentally determining how one parameter depends on any number of other parameters. And again, you always take that dependent variable, the thing that you think depends on other variables, you put that on the vertical axis, and you put the independent variables, the ones that you can change as you want with no repercussions, basically, you put those on the horizontal axis. And then you try different powers until it gets a straight line. Once it gets a straight line, then it's y equals mx plus b, where y is the dependent variable to whatever power, and x is the independent variable to whatever power you graphed. Does that make sense? So in this lab, we're assuming you've learned all that now. You know all these neat techniques. You know how to graph. Graphing's better than taking the average, because there's a linear regression process specifically for linear graphs that gives us really the optimal best fit for all the data we take. Whereas when you're taking an average, you're sort of just counting them all equally valid. And that's sort of problematic. And it can be even worse if you have different errors. So the linear propagation or the linear regression tool actually has the ability to adjust if there's more error on one data point than another, and then a way less error on a third data point, then you can make that one have a higher weight. So there's ways to even take that into consideration. So really graphing is a way, way, way better technique than just taking the averages of all the, you could just take, I found that T is directly related to L to the, 2 power. And you could just take every value of T and divide it by each value of T and divide it by L to the 2 power and get a value for the slope. And then you repeat that over and over and over again for all the other trials, and you get an average slope. Well, you get several slopes and you take the average, but that's not as good as graphing. That's what I'm trying to say. Okay. So with you having learned all these techniques and having not really had to write a lab report, this is our capstone lab, sort of late in the first semester. But the idea is now you have an idea of how labs are supposed to be written. Ideally, we haven't gotten there yet. Ideally, we'd also have a way of doing error propagation, which I'm slowly implementing in this course. You've seen a little bit of it with the error propagation worksheet I gave you guys. Many of you, by the way, haven't turned in, so that's going to be a 0. But anyways, those error propagation things are something that would ultimately come. But that would, with this lab, you're going to actually see how do we write a lab report and how do we do analysis. So in this lab, we're going to have you as students group up into your normal groups, or you can try a new group if you'd like. That's fine too. But if I see the groups getting too big and some groups getting too small, I'm going to just start taking small groups and throwing them in big groups and stuff like that, or making small groups together into a bigger group, just so we have at least 3 or 4 people in each group. Now, when you're doing that, I want you guys to help each other think about what data you're going to take, But ideally, what's going on here is each of you are coming up on your own with what data you're recording, what kind of data tables you should make, and all this stuff. And it's all going to be about springs. And the lab actually tells you, hey, you know, here's one way to determine a spring constant of a spring. We know that Hooke's law says if you get rid of the negative, F equals Kx, right? So if you hang a force, mg, from a spring and you measure its stretch, then you could ideally divide the force, the mg, by the stretch, and that would give you the k value. But again, that would be doing it over and over and taking an average, where a graph would be a better way. So you can think about that. You can think about what variable is going to be on the vertical axis, what variable is going to be on the horizontal axis. In some sense, there's not really any wrong answer, except that, you know, the vertical axis is always, always, always the dependent variable, and the horizontal axis is the independent variable, the one that does its own thing, in other words. So other than that, there's not really a wrong answer. It's just going to mean more work if you choose it stupidly. Okay. Or I shouldn't say stupidly, I should say maybe ignorantly or not thinking ahead. Same thing with another version. There's another way to go about getting K, and that is, it turns out the period is related to the spring constant of the spring through a very specific equation. And if you figure out how to graph that and raise the different variables that you put on the graph to different powers until you get a nice straight line, then you can again put that equation that you ended up graphing in comparison to y equals mx plus b and figure out how that slope can let you get k. Okay, so this is supposed to be the lab where you independently come up with your own data tables. Each of you individually come up with your own tables, but you then confer with your lab partners about taking data, recording data. So each group will have their own set of data, and everybody in the group will have a data set that matches everybody else in the group. And in fact, since we're doing simulations, the vast majority unless you choose different numbers of oscillations or stuff like that, or different masses, y'all could very well have the exact same data. Okay, but the main thing is, at that point, all the analysis, y'all can talk back and forth with each other to get ideas, or to ask questions, and you know, throw ideas off people's for reflection or whatever and stuff like that. So that all works, and you're allowed to do that. But really, once that's done, you are writing your own lab report, you yourself. That means each of you is going to write a lab report. Each of you is going to write a separate lab report from everybody else. There shouldn't be any plagiarism, so there shouldn't be a lot of overlap of actual sentences from one lab to the next, especially if they're in different groups, much less if they're in the same group. So let me first go ahead and show you the lab document. We're using this one that's posted as opposed to the lab manual document. And I'm going to click on it and show you what it says right quick. It's got a skeleton version of what a lab report's supposed to be. I don't necessarily agree with all of it, but it works fine, so we're going to use that. It says we have low system resources. That's normally either Wi-Fi or computing power. So normally this lab would say you need a bunch of equipment, because we'd be doing it in the lab, and each partner would do a different job, and you would have to record all that stuff. This one, everybody's doing every part. Okay, you shouldn't be taking data from someone else that they collected. You should be collecting your own data simultaneously. Don't let me forget, by the way, to make sure you guys can share the screen with each other. But anyways, in this lab, you will determine the spring constant of a conical spring using computer graphing as part of your analysis. You'll be given the theory that applies and some general guidelines. The rest of the lab is up to you. You will have to decide what data to collect, how to make your graphs, how to present your results. A single report typed with sections detailing equipment, procedures, data, graphs, analysis, and conclusion will be the outcome. So here's the theory. The static method says that when you hang a mass M from a spring, that creates a force M times G, where G is 9.8 and mass has to be recorded in kilograms. That actually creates a force M times G in newtons. And that force should be equal to some constant times the stretch of the spring, which they call delta Y, which should be measured in meters. So you can see that the K is supposed to have units of newtons per meter, right? The dynamic method is basically if the mass M is displaced downward slightly. In other words, you never want to go out beyond the elastic region or the elastic range of the spring, and then release, the mass will oscillate up and down and about its equilibrium position. And the period of this oscillation, i.e. the time from, let's say, its highest point to its lowest back to its highest, or from its lowest point to its highest back to its lowest, or you can say from midline to its lowest, back to the highest, back to midline. All of those are equivalent measures of the period. So you can see one of them is like a cosine graph. That one, it went from the highest to the lowest, back to the highest. That's a one period of a cosine graph. Another one's actually a negative cosine graph where it went from its lowest to its highest, back to its lowest again. And the other one's a sine graph. Of course, a negative sine graph would work as well. But either way, the important thing is to realize that that little part, the characteristic drawing of a cosine graph, the characteristic drawing of a sine graph, the characteristic drawing of a negative cosine or a negative sine graph, that's the length of one period. But here's the problem. This says that the square of the period is equal to 4 pi squared over the spring constant times m. So you've got to figure out, each of you individually need to figure this out on your own and then confer with your lab partners to see if they agree. But the main thing is at least each individual make a hypothesis about what you want to graph, what powers you're going to use, and what the slope will be. And then you confer with your other partners to make sure you are all on the same page. That's wonderful. And I encourage you to not be worried about being wrong. You know, a bad hypothesis, a incorrect hypothesis is not really a bad hypothesis. We've learned way more from science from wrong hypotheses than we have from correct hypotheses. So it's definitely something you want to think about. Is a hypothesis being wrong is not an insult to your intelligence or anything like that. Okay, but do figure that out. You want to know what you're going to graph and all that good stuff. And using this method, again, both of which I'm giving you the big hint, you have to use graphs. Okay, so both of these methods, you're going to have to use graphs, and you're going to use the graph and the curve fitting, which will obviously be a linear curve fit, to compare the equation that you graphed versus the equation they gave you in theory, and figure out what part of the graphed expression that the linear regression of XL gave you, what part of it can allow you to calculate K and how you have to calculate K. That's all stuff you got to figure out all on your own. Okay. So here's the guidelines. Collect data based on 2 equations above. You use Excel graph and determine slopes. Use the slopes to obtain 2 independent values of the spring constant and compare these values and give your best estimate for K. Okay, there's actually a way, remember, when you can't just look up a quantity like G, there's ways you can compare how close 2 quantities are if they're not something that are tabulated somewhere. Does anybody remember what tool you use to see how close they come?
R squared.
The R squared does a graph, that's correct. But what about the actual, like, how would you compare your 2 Ks? Would you want to use a percent error there? You know, percent error is something you do for if you're determining G, or you're determining large G, the gravitational constant of the universe, or if you're trying to determine, say, the mass of an electron, you can look up the mass of an electron, so you can compare your mass to what your experimental mass was to what the accepted value is. That's a percent error. What do you do when the 2 values are just supposed to be equal to each other, but aren't tabulated somewhere in a fancy book? Anybody remember what that method was?
Relative error.
Yeah, I think you heard. I think I heard him say like relative error or percent difference. Type
Yeah,
thing.
relative error, relative percent error.
Yeah, it's basically the difference of the 2. You take the absolute value, so it's always big one minus the small one, divided by the average of the 2, and then move the decimal 2 places to the right to make it a percent. So that's something you want to do as well. You're going to use this PHET simulation software. There's a link. Hopefully that'll work. It tells you about playing it and what part to click on, the lab part, for instance. It also says if you have any problems, you might have to actually download the software. I've never had anybody have any problems. I think, well, actually one time I think somebody did, but anyways, what they're telling you here is, let me read this last sentence. This setup has been made for a slightly different lab than we do. at TCC. So in order for you to do this lab, you will adjust the mass of the orange mass, which is initially at 100.0 grams. So you'll look on there and there's an orange an orange mass, and it's 100 grams. But you got a little slider thing up here you can see where you can adjust that. And what it wants you to do is it is recommended that you use at least 5 different masses. If you're wanting to, really knock it home, then try even more masses, but 5 is the minimum. Okay. And they recommend you stay between 60 grams and 250 grams. Okay. You also need to know that the ruler on the right hand side is a meter stick, so that 10 and 20 refer to 10 centimeters and 20 centimeters respectively. And also you should be able to measure to the nearest 10th of a centimeter. In other words, you should get 1 decimal place on these measurements. Okay. Even if you read it as 16.0, you better write down 16.0. This is a capstone lab. You're going to lose harshly if you don't make if you make those kinds of mistakes this late in the game. Okay. So even if it's 16.0, you better write 16.0. All right. Note, it is good experimental practice to never measure from the end of a meter stick. The end could be mangled, which would lead to incorrect measurements. And this one we started at 10 centimeters. So that's good practice. The lab's going to want you to, one, discuss the parts that each person does in your lab group, because you're going to put in on the cover page not only your name, which is the main name, but you're also going to have all your lab partners' names first and last on the cover page. That's necessary. But every one of you is going to do every part, and every one of you is going to take each part that you did and compare it to the person that did it as well. So in case one of you made an error, not everybody's going to make an error. Someone's going to catch it and figure out which one's the right one. Okay. So that being said, it also asks you to, make drawings or sketches or take pictures of the equipment used. You can take pictures of the screenshots used for each of the different types of labs that you're doing here, and that's fine. So if you want to take a couple pictures, maybe one of the static method, making a measurement of delta Y, and then another one of the dynamic method, making a measurement of period, so on and so forth, that's good. So that's how you're going to translate this into doing it with a simulation. Additionally, you may find that precisely measuring the period of oscillation for each of the 4 masses is riddled with reaction time errors, even when using slow motion and the period trace. There are at least 2 ways that can be addressed. 1, measure each period for a given mass 5 times and take the average. Or 2, and this one is the one I recommend, or start the stopwatch when the mass is at the bottom, and then the next time it returns 1 period has gone by. Next is 2, next is 3, so you can do a buttload of periods, say 10 if you wanted to, measure that whole amount of time from it starting the bottom and the beginning of the first period until it gets back to the bottom at the end of the 10th period. And then you've taken that reaction time error and spread it over 10 different periods. If you do it that way, then you just take the total time for 10 periods, divide that by 10, and that'll give you the number of the actual time for a period. Okay. So that way is probably better. And of course, the more periods you use, as long as you don't lose count, the better off you'll be. But and it's still good to do multiple measurements of it just in case there's any error or anything like that. So you could do maybe 3 or 5 measurements of 10 periods and then record each of those 3 or 5 and take the average, and that'll be the period that you do for that particular mass quantity, assuming that's what you're going to be comparing it with. Note, the simulation software allows you to adjust the spring constant by use of a slider. However, we want you all to use a spring with the same spring constant. For that to be the case, make sure the spring strength 1 slider is centered on the 3rd thin tick mark from the word small. So you'll see there's a word small, there's a word large. It says spring strength 1. And this is the little slider. That would be the first tick mark, second tick mark. It's on the 3rd tick mark. That's an absolute necessity. You all got to have the same spring constant. So if y'all don't all put your spring slider on that spot, you're going to have problems. And now this sentence right here is particularly important. I've had a lot of people get confused because they didn't listen to the sentence. So finally, in order for the period equation to work out properly, you must use meters, kilograms, newtons, and seconds. Assume gravitational acceleration. For some reason, it's saying 9.81. That's fine. I usually use 9.80, but 9.81 will be fine for this lab. The main thing is, notice they had newtons there. Okay, so I don't want anybody plotting in the static method. I don't want anybody plotting mass versus stretch, because the spring constant is supposed to be in newtons per meter, not kilograms per meter. Okay. Now down here it says report guidelines. All text should be typed. You're not technically typing it a lot, not on the typewriter anyways, but you are going to turn it in as an electronic file. Again, we're going to use it in do it all up in Word, get the pictures and graphs and data tables inserted in the right spot that you like, make it look really good, get things centered, make sure they're big enough where I can read them on the page. When everything's just perfect, then you're going to save it again as a PDF, and that's what you're going to turn in. But it says here are the parts, the cover page. On this cover page, you indicate your group or table number. You can use our breakout number room if you want. So our breakout room number. I don't really care if this number is there. The main thing I want is the list of all members in the group arranged alphabetically. Okay. This is, and also I want to make sure on your cover page, you put the title and then put your name under it. So I'll know which one's doing that. Of course, you're turning it in a slot that's associated with your name in the grade book. So that shouldn't be a problem, but still that's the way it's supposed to be written. You got to have the title with your name under it as you're the person doing it. The purpose in this, you're going to make a brief statement of what you're trying to determine and also include the theory underlying the experiments. I'm saying, yes, you do that. Okay. So you want to give a brief introduction to the static method and Hooke's law. You want to get a brief introduction to how we know the period is given by that formula. We've covered that recently in class, for instance, or we will again today. So that's all stuff that is included in there. I usually make this what we call like a intro or something like that, where I say, I tell my students to do what they did, how well it was, and what you used, or what you did, what you used, and how good the data was. So that's another thing that's often put in what they're calling purpose, but I call it intro. In the equipment, please make a thorough listing of equipment used. Include sketches, pictures, static model, labels, sketch, blah, blah, blah. Well, again, this is where I'm telling you, just take screenshots of the simulation software and put, sorry, we had to use simulation software because of a giant pandemic where we're all going to die. That don't say all that, but that makes it sound more exciting. All right. Note, 2 different procedures are used in this lab, static and dynamic. You may follow steps 4 through 8, treating parts together, or you may apply steps 4 through 8 to each part separately. Yeah, I agree with that. Procedure. This is one of those things where you're going to do that boring English assignment where you're going to write, how to make a peanut butter and jelly sandwich or something. But you be very specific, and you take all the personality out of it. So you don't want to use sort of like, I did this and Johnny did that, or you don't use proper names and all that good stuff. So you just write a very detailed procedure of exactly what you did. And remember, once you leave the group and you've got your data already, you can always go back into the simulation software and do it again so that you can better help write out your procedure. But I want a very specific procedure, telling what button you clicked and all that good stuff. And part 5, this is supposed to be show data, show all, it's called data, but it says show all data in tables with units. So remember, anytime you have a number in a lab, unless that number is a pure number, and almost never is, that number should either have a unit right next to it, or it should be in a column that has a label with the unit above it, or in a row that has a label with the unit next to it. Okay. That's really just supposed to be data in the data. So make sure you do that. I don't need any calculations or anything like that. It just is supposed to be the raw data. And normally when we take data, it's supposed to be taken in pen. And if you ever make a mistake in recording, you're supposed to draw a single line through it so that everybody can read what the original number was, including you, and then write immediately above it or immediately next to it or below it what the correction is. Analysis. Explain why you graphed your data as you did and how you determined the K values from the graphs. And you must determine K using the slope of the graph data. For examples, see Lab 7, section on pendulum, time versus length, and Lab 8, section on time versus distance on an air track. Calculations, show all calculations completely. Again, if you're taking averages, show me 1 and that'll be plenty. If you're taking a percent error or percent difference, show me 1, that'll be plenty. But you should show me all calculations of how you use your slope to figure out K, and all the calculations should include the actual units in it. Okay. If a quantity was determined with only one method, compare to a standard using percent error. If a quantity was measured using two different methods with no known standard value, compare using percent difference. This is the quiz question I gave you earlier. So that's the whole lab in its entirety. It really is pretty straightforward. I'm going to stop sharing the screen now. I'm going to make the breakout rooms, and you guys are going to choose them like you've been doing recently. And I'm going to act like the auctioneer that's going to announce exactly who's going to where so everybody can follow. First off, I'm going to set the share screen so that everybody can share. It now says multiple participants can share simultaneously. It looks like we got 12 people in here. So I'm going to make breakout rooms, and it looks like I'm going to make what? 4 of them, but I'm hoping some more people will come. So I'm going to let you guys choose. And if you ever get your lab group gets down to 2 people, then I am going to go in and move you to another room. Okay. Actually, I'm going to go ahead and do 3 rooms. And remember, I'm going to be an auctioneer. I'm getting ready to pause the recording, but I'm going to be an auctioneer and say, you know, such and such student went to room 1 and such student went to room 2. Up now, such and such student went to room 3. There are 11, not 12. Oh, yeah, thank you. Yeah, actually, one of my other students came in from another class. I told them they could come in and ask questions once I get you guys started off in your lab. So I will be out here the whole time, and y'all take precedent, but I am allowing students to come in to ask any questions they might have on homework from my other classes. So I'm going to let participants choose. I've created the room. I've opened all rooms.
Gave us during the answer for one of the questions.
Okay.
And I got a different answer than the one it gave.
Okay, which is this something that I gave y'all yesterday? Or are you talking about something from one of the homeworks? You can share
Something for last time.
Okay.
Yeah, I will. One question we did.
Okay. So reference frame S prime moves at speed 0.87 plus direction with respect to reference frame S prime. The origin of S and S prime overlap at t equals 0, X prime. Okay, so yeah, this is the weird part. Did you remember I actually gave you the equation that they're using for this? They said, first off, what was part A? Refresh my memory. I think they just wanted to know what X was, given that our X prime was 120. Yes. And they gave us that S reads 1.5. So here's the weird part about this, and this is critical for you to understand this. S reads 1.5 microseconds. That's the time in the S non-primed frame. Okay. So what they gave you was T, not T prime, but T. And if you look at your Lorentz transformations, you have, for instance, X is equal to gamma parenthesis X prime plus V T prime. So you can't use that T in there, right? But it also gives you that T is equal to gamma parentheses T prime plus V X prime over C squared. And that's good too. So you could actually get T prime, or you could actually get T, but they already gave you T. So if you flip that V and make it a negative, then you can make that X regular X and that X prime into a regular X and that T prime into a regular T. And then you can solve for that first. So let me show you, can I borrow the screen for a second?
Yeah.
It's easy to say, but it's easier to understand what I'm talking about when I'm actually writing it for you. So the Lorentz transformation equations, oops, I hit the wrong button. I'm trying to, there you go. So the Lorentz transformation equations are X is equal to gamma X prime. Notice everything on the right side is going to be prime plus V T prime. Y prime, or Y is equal to Y prime. Z is equal to Z prime. Well, let me write Z. And then T is equal to gamma again, T prime plus Vx prime over C squared. What they gave us was that X prime is equal to 120 meters. They want X equals question mark. And you can obviously put in X there, but you don't have T prime because they also gave us T was equal to, I think it was 1.5 microseconds.
Yes.
So we've got this, but we don't have this, and we want this. So this is our question mark. So on this side, we've got something where I could put t, I could put the t here, but then I have to solve for t prime. And of course I know x prime. So I could actually take all this and solve it. Or you can just realize that the equivalent of this is t prime is equal to gamma. And all I have to do is replace this v with a negative and get rid of the primes. And the thing that don't have primes, put primes on them. So now this will become t minus vx over c squared. So since you have t, you can plug t in there, which is this guy. Okay. And you have, you don't have x. So that's another problem. You actually have to solve for x if that's the case. So you can either do it this way, or like I said, you can solve this one. If you solve this one, it's actually not that bad. You say t over gamma is equal to t prime plus vx prime over c squared. What you're really wanting is t prime. So I'll say t over gamma minus vx prime over c squared is equal to t prime. And that actually works. You can actually take that as is. Now you have a way of finding out what t prime is just by knowing t and x prime. Okay. And they gave you, by the way, they gave you that v is equal to 0.8
was 0.
c. So gamma, of course, is equal to 1 over the square root of 1 minus v over c squared. So now you have everything you need. This way I thought was going to work out, but in looking at it, I don't think this is the best way, just because you're going to get up here an expression for x. And if you plug this in, you also got x on there. So you're going to have to do even more algebra, and you don't want to do that. So what you really want to do is take this expression maybe and plug it in there. And I think that's what they had tried to do when I showed you the equation that the solution had. I think they actually did that, but I hadn't worked out for sure all the details to make sure it matched. I just knew it wasn't the same as plugging this in there. But in retrospect, now that I see it, I was like, yeah, you shouldn't, because that's an x instead of an x prime. So why don't we give that a try? Let's first calculate what t prime is.
Okay.
So I'll say t prime is equal to t, which is 1.5 times 10 to the negative 6 seconds. Our gamma is going to be 1 over the square root of 1 minus 0.87 squared. So let me figure out what that quantity is.
Should be like 2.028, if I remember correctly.
Okay, that sounds about right.
Let's just check.
2.028, yes. And I'll carry maybe an extra digit, so 282, say. Okay, so I'll say this is over 2.0282, and then I'll say minus 0.87 times, you can just use 3.00 times 10 to the 8th meters per second here. Now I got to multiply that by x prime, which we said was 120 meters. And now I got to divide that by 3.00 times 10 to the 8th meters per second, only it's got to be squared. So I'll do 1.5 e to the negative 6 divided by 2.0282. I'll say minus parentheses 0.87 times 3 exponent 8. I'm not even taking the time to calculate to cancel out the c's. I'm just going to do it times 120, and then I'm going to say this is all divided by, I'll put parentheses around it. Actually, I didn't even need to. C squared, and this gives me 391.57. Remember, I'm using a calculator in engineering notation. 57 times 10 to the negative 9th seconds. Notice that works out to be seconds. This is meters per second times meters. That's meters squared per second divided by meters squared per second squared. So that just gives me seconds on top. So that's what my t prime is. Now I can plug in my t prime into the expression for x. And in that case, I'll get 2.0282 times x prime, which is 120 meters, plus 0.87 times 3.00 times 10 to the 8th meters per second times t prime, and t prime is 391.57 times 10 to the negative 9 seconds. I'll put this in a square bracket instead of a parenthesis. So I'm going to say times 0.87 times 3 exponent 8. I'll say plus 120. So I got 102 added to 120 there. And then I multiply that by 2.0282. And I get 2.0282. Oh, nope. I don't know what happened there. Oh, 2.0282. I said multiply, but it chose to just write the number down again. Like, that's a good thing. So I get 450.666. That one turns out to be meters, and obviously that's a lot more sig figs. So does that make any sense to you, Jacob?
Yes. So that would be the answer for the second part?
The second part asked for X, or no, the first part asked for X, didn't it? I can't remember.
Both asked for X.
But one was what, X prime?
Oh, that was the second part's answer. That's the second answer.
Okay, that makes sense.
So yeah, the first one was Galilean.
Oh yeah. A lot different from Galilean, ain't it?
Okay, so that makes more sense. Yeah.
So you put like 451 meters or something?
Yeah.
That's cool.
I put 450, but it gave me it.
Gave you credit. That's cool.
Okay.
What next? Feel free to share your screen again.
Okay. Yeah. That was the one question that else had. We still have 3 more for this section.
Okay.
They look like they're all one part, hopefully.
Yeah, those multi-part ones, they really kill you. You're like, oh man, but they're so helpful because they're usually telling you how to do stuff. Okay. In
It's
its
really
own
helpful
reference
having
frame, a
you
box has the shape of a
showing.
1.8 meter cube on its on a side. So basically, a cube means it's 1.8 by 1.8 by 1.8. The box is loaded onto the flat floor of a spaceship, and the spaceship flies past us with a horizontal speed of 0.90 c. What is the volume of the box as we observe it? Okay, that's a good question. I like that. So let me draw a picture for you real quick. I know the numbers. It's 1.8 and 0.90 c. Okay, so if I can steal the screen again. So
I gave it back.
Yeah, thank you. What we have is a box sitting still, or if we're in the spaceship riding it, then we're moving the same speed it is, but we read this width as 1.8 meters. We read this length as 1.8 meters, and we read this height as 1.8 meters, right? But when
that's the first thing I wrote down.
Yeah, but when we look at it flying by us, what we see is a Lorentz contraction. So we're still going to see this height because that's perpendicular to the velocity. We're going to see that height stay the same. So it's still 1.8 meters tall. And this width, which is also perpendicular to the velocity, that's going to stay the same. But this is going to be Lorentz contracted, and that's going to be 1.8 meters over gamma. Once you have that, then you can multiply the 1.8 times 1.8 times this, and that'll give you the volume.
Okay. So that's 1.8. That's 1. I'm just writing the second cube right now. I messed it up the first time.
No problem. I get a gamma factor of 2.2942.
Well, and I will get my answer. Wondering what I did wrong. I forgot 2.2942. Yep. Okay, and then you just multiply it, right?
Mm-hmm. So it went from 5.832 cubic meters to about 2.5 cubic meters.
Wow. Let me plug that in.
The big thing to know about this is always keep in mind that it's only the direction parallel to the velocity that gets contracted. The velocity we're assuming is going this way. So it's only this dimension that's parallel to it that gets contracted.
Since velocity is going that direction.
Yeah, exactly. It points the direction, I should say. The velocity.
Okay, yeah, I understand that because yeah, so it's kind of like with the ladder problem where the length of it was expanded and contracted, but the height of it stayed the same,
Right.
and the width of it would have also stayed the same, even though
Exactly.
it was a
The boy would
two-dimensional
have been the
problem.
same height carrying the ladder. He'd be the same height running as he was when he wasn't running, assuming he was in the same, crouch position. But he would be narrower. He'd be skinnier from front to back, and the ladder would be shorter from front to back.
Yeah. Okay. This chapter seems a bit easier than the others.
Yeah, the relativity, we try not to get you too terribly hard stuff, but at the same time, we want it enough to get you where you're like, wow, that's kind of interesting. Maybe I should consider a major in physics.
Yeah. Okay, I have the next problem. I'll share
Okay.
screen.
No problem.
Oh, now.
Oh, cool. The Enterprise. An observer sees an alien vessel approach at a speed of 0.6 c. So V alien is 0.6 c. And they did do 60, so I included that. The Enterprise comes to the rescue and overtaking the aliens, moving directly toward Earth at a speed of 0.90. So V Enterprise is equal to 0.90 c. So I got that. What is the Enterprise's relative? What is the speed of the Enterprise relative to the alien vessel? You think you know how to do this?
Wouldn't you just subtract them?
You want to be careful. In Galilean relativity, there's simple cases where you can add and subtract. But remember our rule, what I taught you is in one dimension, it's really wonderful to say velocity of A as seen by C is equal to the velocity of A as seen by something plus the velocity of that same something as seen by C. So the main thing is this one and this one have to match that one, and this one and this one have to match each other. So we could, for instance, say B and B. That's Galilean relativity. The difference between Galilean and special relativity is now you've got 1 plus VAB VBC over C squared at the bottom. So what we have is the alien craft measured with respect to Earth is 0.60 c. And I'm going to say the alien craft, which is headed towards the Earth, and the Enterprise, which is headed towards the Earth as well, are both in the positive direction. So we also know that the velocity of the Enterprise, ooh, that's bad. Let's do velocity of that with respect to Earth, and the velocity of the Enterprise. That's the actual symbol that we use in astronomy for the Earth. So the velocity of the alien craft with respect to Earth is equal to 0.60 c. The velocity of the Enterprise, which unfortunately started with an E, as seen by Earth, is 0.90 c. And what we're asked is, what is the velocity of the Enterprise with respect to the alien craft? Am I right on that?
Yeah.
So normally, like you
Enterprise
said,
to the alien.
you'd say, yeah, the 0.9 minus 0.6 give you 0.3. So that's how much faster it's going. So if you were going on the road at 100, let's say at 60 miles per hour, and someone's coming up behind you at 80, you do 80 minus 60, and you say, oh, they're coming up to me with a relative speed of 20, right? So that's what you meant by subtraction. And that's exactly right with regards to the stop half. But we want to know it relativistically. So what we're going to say is we want to know the velocity of the Enterprise as seen by the alien craft. So getting your subscripts is really the most important part. Now, see if you can use this to put over here and then find the right expression for the right-hand side. See what you write down and let me see it. Or tell it to me and I'll write it out as you tell me.
So you want me to plug in the VEA into that equation?
No, I want you to make the correct equation using this pattern that I just showed you. I want you to use write out the correct equation for this.
Okay. Yeah. Okay. So would I include? Wait, no. The B would become A, correct?
Yeah, the E is taking the role of A now, but that's a really confusing way to do it. Just remember your rule. You need E and A, so that tells you what the outer subscripts are, the first one of this one and the second one of that one, and then you just need the inner two to match.
Okay, so it would just be V of EB, you could say, right?
Yeah, we don't have a B though, but yeah, V of E, V sub E, and then something. Leave that blank for right now. Put your plus symbol, and then what's the next one going to be?
V of that blank, and then
So what's the second subscript got to be for this guy?
A.
Right. So now all we need is something that we have, or something that we have here. So do we have anything with E as the first subscript, whose numbers we know?
The Earth.
Yes. So you can put the
Okay.
circle there. And notice that causes a little bit of problem because we don't actually have the V of the circle A. We have the V of the A with the Earth, right?
Yeah.
But remember how we dealt with that? You recall how we dealt with that? There was another rule that I warned you about. And it's sort of like if you pass me coming towards me, okay, my velocity is 60 miles per hour. And let's say you're sitting still, okay? So in my frame, you're going 60 miles per hour in the negative direction, but in your frame, I'm going 60 miles per hour in the positive direction. So what I'm saying is the velocity of me with respect to you is negative 60, but the velocity of you with respect to me is positive 60. So do you remember any rule about if you transpose?
So would that mean you'd have to change it?
What's that, Jacob?
So would that mean you have to make it negative?
Exactly. So we now say VE this minus VA this over 1 minus VE Earth VA Earth over C squared. Now you're good to go.
So then you can do it.
I think if you have a child, or is that like a little sibling? So I
That's a
thought you
little
were-
sibling.
Okay, I was gonna say, because I thought you're like a high school dual enrollment.
I graduated last year from high school.
Oh, okay. Sorry, I was thinking you and your brother were both like dual enrollment high school students.
So you get 0.3 C, right? Yeah,
For the top, right?
over, yeah. Then that'd be over 0.4.
0.9 times 0.6 should be 9 times 6, which would be 54. And then divided by 100, that'd be 0.54. 1 minus 0.54 would be 0.46. So
Yeah, and it wants it in the C.
mhm.
The 0.3 divided by 0.46.
And I get
That's correct.
0.652.
That's correct.
Yep.
And there's a
Easy peasy,
second
right?
part, which is the opposite way. What is the speed of the alien vessel relative to the Enterprise?
Speed of the alien vessel with respect to the Enterprise, right? So you know what to put there, right?
So would you do? Yeah, you would just do pretty much the same thing, just mainly flipping stuff.
Yeah, in this case, we already have VEA. They want to know VAE. What's the difference between VEA and VEAE?
You just got to make it negative.
Exactly.
Telling me to check my signs. Oh, that's why. Wait.
Now, if it says speed, you can actually put 0.65 probably, but if it says velocity, you need to put in the negative. So that could be a problem. I don't remember what the wording was.
Velocity absolute, it says.
So
It says
then they probably
velocity
just mean-
absolute.
maybe they just mean 0.65 then, as opposed to
Yeah, they got me that one.
turds.
Yeah. Okay, and I think there's just one more left for this section. Yes.
Surprised I had like 8 people that wanted to show up. I was hoping the more people would show up. But you can sit in for your brother, so at least you're helping him. But he even didn't say he was coming. I just sent it to him just because I figured y'all might want to both be here.
Yeah, I think a lot of people got it.
Yeah, I,
Someone,
I couldn't remember if Elizabeth wanted to.
someone asked like what it was.
There's some place where
Okay,
you guys are meeting and plotting a coup, isn't
here- Yeah. So I'll show you the next one now.
there? Okay. I'm slowly trying to give you less hints and see if you can get it on your own. Trying to teach it, in other words. So rocket A passes Earth at a speed of
Yeah.
0.74 C. It says VAC, a VAE, I guess, and that's 0.74 C. At the same time, rocket B passes Earth, that's VBE, moving 0.82 in the same direction. So this case is 0.82, also positive. C. How fast is B moving relative to A when it passes A? Okay, so you think and notice they're doing U over C here. So they're really asking for beta. That beta is the part that like the 0.74, the 0.82, in other words, the part without the C. That's what beta means. So, or that's what U over C means. So can you write out that equation? They want to know what the velocity of, what is it, A as seen by B, or did it say B as seen by A? Do you recall? I got it in my explaining mode.
B seen by A.
B as seen by A. So we want the
Oh, sorry.
velocity.
How fast is, yeah, how fast is B moving? Oh, no, never mind. Is B moving relative to A when it passes A? So it
Okay,
would be B seen by A,
exactly. So VBA is what
right?
you're looking for. Yep.
Okay. Okay. So do I just use the equation we used for the last question?
Well, you got to make a new one every time, basically, because you don't want to get confused in trying to
Well, yeah.
memorize that. You want to memorize the pattern, which is inner and outer match the outers, or the first and last match the outers, and then the inners match each other. So what do you think that is going to equal?
VBE.
Yep, that's what I go with.
So then it would become minus VEA,
It would be plus VEA,
considering we have to, oh, plus VEA.
right? And we have VAE. That's what I think you're jumping ahead to do.
Yeah.
I'd say about 0.2.
Okay. So the U over C, can you explain like what the,
So your book used U
understand.
where I used V here. Your book used
Okay.
UVA, UVE, UVA, that sort of thing. So that's why they're using U instead of C. And then basically what they're doing is saying, okay, take this answer that you get and divide it by C. So if you divide that by C, you just get the 0.20346. That's another word for
Okay.
beta, by the way. So if you run into that, that's another thing you might need to know. That's defined to be beta. And it's a unitless
Okay.
quantity.
Gotcha. Yeah, that confused me for a second. Yep, it was correct. So I
I'm
believe
freaking
that's
brilliant, man.
what?
I said, of course, I'm freaking brilliant, man. I'm being funny.
Yeah.
Anything else? You seem to be getting it a little better. I think it's a lot of it's just about the terminology and having never done anything with relativity. So, keep an eye on when it says the energy of a particle is some number of GeV or MeV or TeV. That means the kinetic energy. And then as long as you keep that straight, then you can always calculate, the momentum, the gamma, the total energy, all that good stuff.
Okay. Yeah, I have the second section to do, but I don't know if we'll be able to do it during this time, or
We still got like an hour, at least. If you're interested, I can still help.
is it possible for us to start it?
Yeah, no problem.
Because I haven't been able to start this one yet. So I'll share screen. Do you want to like stop the recording and start again since it's a different?
No, I just keep it going. It's cool.
Okay.
Okay, let me read that real quick. Hold on a second. I gotta check something else too out. Make sure my students are good to go.
None of them have popped in yet. Are they on the same lab that we are?
Yeah. Did you have lab yesterday? Or tomorrow?
Yeah, I did.
Yeah, they're doing the same lab.
Did I?
Okay, so now let me look at your question now that I got some of that other stuff finished. Okay, so it says to learn to calculate energy and momentum for relativistic particles and from relativistic equations to find relations between a particle's energy and its momentum through its mass. The relativistic momentum P and energy E of a particle of mass M moving with velocity V are given by gamma mv, and notice that E is a total energy. That's not the kinetic energy. Gamma mc squared is the total energy. So that's the key thing to remember here, just in terms of everyday life and solving relativity problems. So it says part A, find the momentum P in the laboratory frame of a reference of a proton moving with a speed of 0.870 c. So part A, V proton is 0.87 c, if I remember correctly. 870 c.
Yes.
That should be a little bit bigger than 2, because remember 86605 was gamma equal 2. And we're going to use 938 MeV per c squared for the mass of the proton. So M proton is 938. Now that's weird. It's going to be weird, but this is what we do. We say MeV per c squared. And if you get more advanced, I'll just drop the c squared and really get you nice and confused. So what we know here is that E is equal to gamma mc squared, but that's the total energy. The momentum is equal to gamma times mv. So what we really want to do is figure out what gamma is. Does that make sense?
So we would go through that normal we have.
Mm-hmm.
Okay.
P is equal to gamma mv. And of course you could say this is the same thing as gamma times, let's say, mc squared over c squared times v. And the reason why I write it that way, basically I just force myself to write c squared over c squared so that I can use this as a mass. So I can actually put that in there. Now all I got to do is figure out gamma and what v is, and we'll be golden. So that's the neat way. That's a way of using it. There's a lot of different ways you can use it, of course. But what we want to do is figure out what gamma is. And of course, gamma is equal to 1 over the square root of 1 minus 0.870. Don't forget to square it like that.
Yeah.
So that little trick might help you a little bit. That's part of the reason I wanted to show you that. So can you calculate gamma?
Yes, I can.
Yeah, it's at 2.82 again that we had, 2.0282. And they actually did 3 sig figs on this. So we really should carry it out to the second decimal place. So I put 2 extra sig figs there on my version.
Okay. I figured it was going to be similar since it was the same. They seem to be keeping that. And then our velocity would be our VP for time, right?
Mm-hmm.
So we just have to plug them in.
Yep. So now you can just say P is equal to, we got the gamma. This MC squared is just plain 938 MeV. And this C squared is the C squared that they have right there. So all of this is just 938 MeV.
Okay.
And the units they usually use for momentum, I didn't catch whether the assignment's wanting it, but what's the unit it's asking for this momentum? Is it MeV per C?
Yes.
Okay. So what that means is now we can do something different.
Yeah.
We can write V over C times C basically, because you're going to put in gamma, which is 2.0282. You're going to put in 938 MeV per C squared. That's the 938 MeV. That's the per C squared. So that's everything right there. Now you're going to say V is 0.870 times C, but you're going to divide that by C as well, because you're going to want the units to come out in MeV per C. So this MeV.
Wouldn't you have to divide it by C squared?
Just C. Energy is MeV per C squared, but momentum is MeV per C. And the reason we know that is E squared is equal to P squared C squared plus M squared C to the fourth. So you can see if you just drop that for a second, you see P must have units of E per C. The E divided by C is the units for P. So it's MeV per C. But notice,
yeah, I'm just confused with in the equation, we do 0.87 by C. That just cancels out the C's, doesn't it?
it does, but you're not wanting to do that. The reason why is this MeV and this C you're not actually going to use, because that's just going to come out as the unit.
Okay.
Right. So you're just going to take
Okay.
2.02 times 938 times 0.870 times 3 times 10 to the 8th. But notice it was originally V. So in that sense, it does cancel out.
Okay. So we just plug the numbers in.
Mm-hmm. Oh, Mary's here.
So I do multiply by the speed of, or the C, correct?
So yeah, the formula gives you gamma times this is MeV per C squared, all this, and then times V. When I forced myself to divide by that C, I had to multiply by C as well. So yeah, you still have to do that. That C's got to be in there.
I got 4.97 times e to the 11 for some reason.
Yeah, that's the same thing I got. Oh, yeah. So yeah, you're not multiplying by that C. Sorry about that.
Okay.
Yeah, you're right about them canceling out. I forgot I'd already taken care of the C squared over here by using that. So yeah, that was my boo-boo. So you should get about 1.655 times 10 to the third MEV, which is really GeV.
Yes, that's correct. Okay. Okay, and then I'll show the next part. What's the total energy?
Are you doing the second relativity assignment now?
Yeah.
Okay. Let me see. This is okay. You're doing this. So part C, I guess. Did we miss part B? What was part B?
This is part B.
Oh,
Part
okay,
B.
okay, got you. Fine. Okay, I see now. I got you. So part B, find the total energy of the proton. Now this is kind of nice because the total energy is just gamma times MC squared. If you take 938 MeV per C squared as the M, then the C squared in the bottom of the units cancels out with that C squared. So you really just have to multiply it by gamma. So the 938 just has to be multiplied by gamma. In other words, let me write it like this way. So E is the total energy, and that's gamma MC squared. But the mass is 938 MeV per C squared times C squared. Notice that C squared cancels out with that C squared. So really all you have to do is say 2.0282 times 938 MeV.
Yep, that's correct. Okay. So does it just want me to solve this equation then?
What is the value? Okay, you can think about it a couple ways. Remember, I said E squared is equal to P squared C squared plus M squared C to the fourth. Well, if you pull the C squared over there, you get E squared minus P squared C squared. Notice that's exactly what they're asking about. And of course, when you do that, that's equal to MC squared squared. So really all you need to do is take MC squared is actually a unit of energy. So you got to take the 938 MeV and then square it. Does that make sense?
And that's okay, and that's it for that question?
Yeah, that's a little bit of a trick because they did a weird thing about it, but yeah.
So if you were to solve this equation using the like numbers, you get the same thing?
Yeah, and that's something you really should try to do to make sure you're right. Of course, the fact that they got both answers right, it means you did, but you could totally take the 1.902 times 10 to the third, square that, and subtract the 1.655. Remember, that's going to be times C. So it's going to be 1.655 and square that, subtract them. So I'm going to do that real quick just to double check. So I just took the 1.902 and I squared it. Now I'm going to take the 1.655 and square it. And now I'm going to subtract them. And you should get the same thing as 938 squared.
Yeah, you just have to multiply by, wait. You multiply by, correct,
Yeah, so remember
and you
P we
square it.
worked out as MEV per C. So if you put it inside
Yeah.
that parentheses P times C, then that C in there is just going to disappear, and all you get for PC is just the 1.655 times 10 to the third. So I did do that. All right, Mary. Mary's here now, so she can ask questions as well. But I also got a good video recording for helping people on the relativity stuff.
I messed up something somewhere. I'm trying.
Did you get 879 times 10 to the third?
No, but I'm pretty sure I know what I did wrong.
Okay.
The numbers I had were like rounded instead. Yep, now I got it. There we go. And then part D is the last one for this question.
Gotcha. So what did they ask you for part D?
They ask for the rest mass of a particle traveling with the speed of light in the laboratory setting.
Okay. The rest mass of a particle traveling at the speed of light. Okay, so for starters, what you see is the rest mass is always supposed to be mc squared. And if it was traveling at the speed of light, I think you can see that that becomes basically an infinite amount of gamma becomes infinite. So this is odd. I'm not sure why they're referencing the lab frame. I'm not exactly sure at all why they're referencing the lab frame. My instinctive answer is that this is not. It should be 0 is what the answer should be. But I'm trying to see what they're trying to make sense of, or how I'm trying to make sense of the lab frame part that they stuck in there.
So the hint tells you to compare the equations for energy and momentum if V is 100% C. Which,
Oh, gotcha. When E is 100% C. So when E is 100%, wait a second. When E is 100%, what was the hint they gave you? Sorry about that.
0.1 C or 1.0 C.
Oh, gotcha. So yeah, the available hint said something along the lines
Reese just.
Professor,
Yes. Yes. What's up, Reese?
I have a question. It's for the dynamic method
Right.
where we have to count the oscillations.
Uh-huh.
Set how far down should we drag the spring? The
Okay.
mass,
So whatever it stretched when you put let's say maybe the middle mass on it, that stretch should be fine past where it hangs. So like if you found that you went between 60 and 250 grams, let's say one of them happened to be about 120 or something like that grams, that stretch should be plenty. So if it was 2 centimeters, go ahead and stretch it an additional 2 centimeters. The main thing is not very much. And I don't think it'll let you do very much either way, so it should work out fine for you.
so 10 centimeter displacement from the line.
Right.
Okay.
That makes
Thank you.
sense. No problem. So here's what I'm thinking. That actual hint did help me a lot. That's the whole reason they ask you for e squared minus p squared c or minus p c parentheses squared, because here I'll show you on my page again. Remember, e is supposed to be gamma times mc squared, right? And remember that p is supposed to be gamma times mv. So e squared minus pc squared should be really the square of the rest energy. So if I actually took the square root of that, I should get the 938 that I had for the proton, and I will, right? You can see that. But if you look at it this way, this is the same thing as gamma squared mc squared minus gamma squared mv squared times c squared. So when you look at that, you can say, wait a second, I got a common factor of gamma squared. I got a common factor of m. So that's gamma squared m squared. And I got c squared minus v squareds left. But c minus v is, for v equals 1.0 c, what do you get?
Wait, wouldn't you also have a c squared at the end? So would you have to take out the c squared?
No, so what we're saying
wait.
is v is equal to 1.0 c. So I'm going to say c squared minus 1.0 c squared. What does that give you?
That would just give you 0.
Yep, that's the answer.
The answer's just 0.
Yep. That's what I kept telling you.
Okay.
It's weird that they bring in the lab frame in. I wasn't really sure why they were doing that. But I kept telling you the answer should be 0. I just don't know what they're doing with the lab frame. But I think they're trying to get you to think in terms of this derivation, and maybe that helps you. I don't know.
Yeah.
Mary, you back yet? Sure, it's not back
Yeah,
there.
that was correct. Good.
Yeah, I am.
Oh, you are? Okay. Did you have a question you want to jump in with? I've answered several of his, so it's definitely your time. Our turn.
Like the lab, I just need help with calculations. Not the
Okay.
Springs one, the other one.
Got you. The previous lab. No problem. Let me go refill my coffee. I'll be right back.
Yeah, no, yeah, I got stuck on the.
So, Mary, are you talking about the projectile lab from last week? Is that correct, Mary? Are you talking about the
Yeah.
projectile lab? Okay. So, you want to share your spreadsheet for a second while he's thinking of his next question? Okay. So that's the lab. Were you able to put in all
Yeah,
these
so-
numbers and get the first 3 lines of that spreadsheet that they show you down, maybe a half page down from here? All right, so
This.
yeah,
Yeah, I'm
that,
calculating it wrong. I can tell because of the muzzle level.
yeah, so you remember A1, they have an example table in your lab. Scroll down a little bit. I think it's 1.2 and keep on. And 1.4, I think, is what they're supposed to have in that A1 and A2 column. Or cells, I should say. Maybe it's a little bit higher than where you were, sorry.
Right here.
Yeah, there you go. So you're supposed to have that 1.20 and that.
So is it actually
1.40.
starting with these numbers?
Yeah, you're supposed to put those numbers in at A1 and A2, and then that number should pop out at A3. And then if you've got the columns B, C, D, and E right, then those first 3 rows should be matching your table as well. So that's the first thing you got to do is make sure all those match. So you got what?
Why are we using that though instead of like the Y that was described here?
Yeah, because the problem you're having right now, you're not getting the right answers. This was a nice little check that allows you to make sure you're getting everything right before you put the real data in, because you need this analysis to be correct before you can put the real data in. Otherwise, you're not going to get anything meaningful. So put 1.2 there. Let's see what you get there. And 1.4. 2.8577, is that what they had for A3?
8.3 they had.
Does yours round
So-
to A3? No, so you're a little bit.
I didn't understand like the formula. What is like, yeah, so it's a math problem.
Yeah, so if you look column,
like where does the A come from here?
the A should be the positive 9.8. That's why you use 10 instead of 9.8.
Why is it 9.8? Because it's gravity downwards.
Yeah, they're choosing downward to be the positive direction. So in that formula for A3, you should have replaced that A with 9.8. There you go.
Oh,
Now you see it's matching. Now also,
yeah.
if you fill in that that cell, the one to the right of it, the one to the left of it, I mean the right of that, and the one to the right of that, then that all that stuff should match.
Okay, I'll do that real fast.
Yeah, go ahead and play with that a little bit and let me know if you have any questions regarding it. I'll be here. All right, how about you, Jacob? You got another one?
Yeah, there's the next one now. I will share screen.
Okay. Proton with a rest mass 1.67 10 to the -27. Okay. Has a total energy 4 times its rest energy. So E equals 4.0 MC squared is what they're saying. Okay. What is the kinetic energy of the proton? And B, what is the magnitude of momentum of the proton? So they want to know K equals question mark and P equals question mark. So do you have an idea what you're going to do here? Formula do you know for the kinetic energy? Do you have a formula for that you're aware of?
I can't remember.
Okay, there's a couple of them, but the one I think is most important is not this one. E squared is equal to P C squared minus, or excuse me, plus MC squared squared. The more important one here, I think you'll see, is E is equal to gamma MC squared. because they said
Okay,
E
yeah,
4.0 MC squared. What are they telling you? What is that 4.0 equivalent to?
your gamma,
Yep.
correct? Okay.
And they ask you first for the kinetic energy. Do you remember the formula for kinetic energy and relativity?
I don't remember relativity.
It's gamma minus 1 times MC squared. Because remember, one of those MC squareds is the rest energy, and the rest has to be the kinetic energy. So that's why they're subtracting 1 MC squared from it. And by the way, since they said it's a proton, we already know that MC squared for a proton.
Equaled the rest energy, correct?
Yeah, that's 938 MeV. So that makes the rest of this quite easy. Let's see if you can figure out from there what you're going to do.
So for the kinetic energy part, I to plug in gamma equals 4 and MC squared is 938.
Yep.
So that would just be 3 times 9.
Yep. And of course, 3 times 938 is in the thousands. So you can divide by 1,000 since they want it in GeVs.
So it's in MEVs and then
Mm-hmm.
looking for GeVs. So it would just be 2.81.
Yep, that sounds about right to me.
That's correct. Okay.
Now, do you remember the formula for momentum in relativity? Well, you remember what it is in terms of classically, right? What was momentum in classical physics?
The relativity is the P equals mu or MV.
Yeah, in classical,
Is
it's
that the one that we were
MV.
using earlier?
Yeah, classical, it's just
Okay, yeah.
MV, but in relativistic, we just add the gamma on the front.
Okay, yeah. Gamma MV. It's a U. I wrote it wrong. It looked more like a U than a V.
Are they asking for, yeah, they're asking for kilograms meters per second. So in this case, you actually have to do the brute force thing, use the 1.67 times 10 to the negative 27th for the mass. You also got to figure out what V is. And of course, remember beta, which is defined to be V over C. Remember that. I've solved this for you before, but it's the square root of gamma squared minus 1 over gamma. Sorry, I don't know why I wrote 2 there. So we already know what gamma is. Gamma is 4. So you do 16 minus 1. That should be the square root of 15 over
4.
4. And of course, that means velocity is that times c. That might save you some of the work by just recalling all that stuff.
Okay.
Tell me what you got when you calculate it.
You have to multiply it by the mass, right? The
Yep.
rest mass.
Yeah, the 1.67 times 10 to the negative 27th.
Yeah. And then multiply by the root 15 over 4.
And then of course times c.
Yeah.
Sorry.
I got 4.85 times 10 to the negative 19th.
It seems like you made calculation error or typo or something. I got like 10 to the negative 18th.
What did I mess up? 1.6 times 27 times the 3 times the 8 multiplied by the root 15 and then by 4. Oh. I see what I did. That one.
Yeah, I got 1.94 times 10 to the negative 18th.
Give me 1 second. What did you get?
1.94 times 10 to the negative 19th, or excuse me, 18th.
Where am I going wrong? Wait a minute. Now I figured out what I did wrong. I
What's
got
that?
it now. Forgot to multiply. I was wondering where that gamma was going.
Yeah, you've got multiplied by 4 then.
Yeah, I realized that. Like, I was like, yeah.
Is that the last part of that problem, or is there something else?
There's one more part. It asks for the speed of the program.
Oh, okay, gotcha. Which you sort of had to work out by doing beta here, because I think don't they want it in terms of C?
Wait, so yeah, they want it in terms of C. So be root 15 by 4.
Yep. You get 0.9682.
Yeah.
Yep.
It let me just put in root 15
Oh,
over 4.
15 over 4. Cool.
Okay.
Mary, you have any questions on filling those formulas in? Or are you matching the columns that were?
Yeah, I'm stuck.
You're stuck. Okay. Pull up your screen again. Let me show you something. Or let me show you the lab first. Or you show me the lab first. Sorry about that.
Let's see.
You can go ahead and pull up another one when you're ready, Jacob. I'm going to look at her stuff right quick. So yeah, we need B6 first. So what they're wanting you.
So I got the B stuff.
Okay. Does that match the table from the lab manual? Oh yeah,
Yeah.
0 degrees. That should be 0. That's right. And does the 23.52 match?
This is normal. That's this. Yeah, these three I'm messing up on.
Okay, so you got the 0, but what's the 4.84 is what you're supposed to have. So that's that final Y velocity. You
Oh
said,
Jesus.
uh-oh.
There you
So
go.
show me your formula that you got in C6. You took B6, which is that, you squared it, okay, plus 2 times 9.8 times
And it says
$$1.
yeah, plus 2AY. Here. There. This
Yeah, that's supposed to be that. Gotcha.
the initial squared plus 2AY.
And they're wanting that to be, what was
And this
it?
is the initial.
The final Y.
4.85. I think.
Yeah, that should be
4.849.
4.849 should be what you're getting, the final Y velocity. So what they're using there is V0, or excuse me, V squared is equal to V0 squared. I think you're missing a square root. All of that should be the square root of all that. So like in front of the B6 that you got, type SQRT and then parenthesis.
Yep. Okay,
There you go.
that's what it was. Yeah, I didn't just solving the equation because of the square root on this side.
Now we need D6, which is they want you to solve for T. So that's
Initial
V.
plus 18.
So in that case, you're doing V final, which was I think the previous line, minus the V0Y initial, which I think was A6, and then divide it by 9.8, and that should give you what the answer for D6.
So final minus initial, everything divided by,
Yeah, put parentheses on that though. Yeah.
and it's just regular 9.8.
Yep.
I think that was it.
I think they had 495 for in the table.
Yep. And then X theory and X data.
Okay, so in this one, they want to know to give the range. So they're wanting the X. So in this case, it's just muzzle velocity times the cosine theta times the time. The time is the previous column. The muzzle velocity is that A3 or whatever it is. But you got to remember cosine theta.
Do you want this in radians again?
Yeah, exactly. That's the main thing. You got to convert it by multiplying by pi over 180.
Or put the radians before?
Exactly. You could do that as well.
Whatever you
There's a
say.
radian function in Excel.
Make them do the math. Okay. Muzzle, cosine, radians, theta.
Remember a dollar sign on that one. Dollar sign A, dollar sign 3.
Yep. That one I got messy.
Times
Times cosine, radians. What are we using as the theta?
Yep.
Oh, 6, yeah.
and times T. Yeah, times D, D6.
Times T. Yep, that'll do it. Yeah.
Yep. Now that table should match once you
Okay,
copy it
next
down.
one more.
There's the rows that the lab manual gave you.
Yep. Those work.
Okay. So now you can go back in A1 and you can put in 10 and you can put in A2 1.43, I think it was, or 14.3, excuse me. And that should now be correct.
If I put 14.3 in here, it'll change all these to mine.
Yeah, in A, well, yeah, you first got to
Gotcha.
copy
So this is just to double check like our math on it.
right. Now that you have that, change the A1
Okay,
in and change the A2 to 14.3.
so this is 10 and this is 14.3. Okay, real fast. I just wanted to make sure it's actually performing the experiment right with my data. Because this one little part here confused me. It said like leave the initial speed at 15, then and then adjust the speed. So I did that, but then after it was like 15, I just kind of kept it at 10 and then I dragged the target to where it would hit.
Yeah, you weren't supposed to change it once you got it to hit the center of the 14.3 target. And
that was the speed you're supposed to leave it at.
Exactly, which turned out to be like 10.016 or something. So if your stuff's right,
and that's why they said you can
red
only use like the
numbers will
integers.
match the column E. I said if your calculations are all right, then those red numbers in the X data and meters, those 14.3, 15.1, 15.9, that will match that column E in your spreadsheet.
Oh, okay. So once I plug in these details, then my X data is going to be the rest of this.
Yeah, those red
Gotcha.
numbers go in column F and they should match the column E.
Okay, all right, I'm gonna try that one now.
Don't forget to change your spreadsheet to 10 and 14.3 though. Okay, you ready for another one, Jacob?
Yeah, I'm ready for the next one. I'll share screen now.
Okay.
Here we go.
Two protons. There's their mass, initially moving, equal speeds in opposite directions. So protons continue to exist after a collision that produces eta minus eta zero particle, and the rest mass of the eta zero is 9.75 times 10 to the negative 28 kilograms. Okay, so let me write those numbers down right quick. I got the mass of the protons 1.67 times 10 to the negative 27th. The mass of the, I think I'm remembering that correctly, that Greek symbol is eta, but it might be new. I don't think it's new. I think it's eta. But anyways, that mass is 9.75 times 10 to the negative 28 kilograms as well. And they're initially moving with equal speeds in opposite directions. The protons continue to exist after a collision, and that produces the N0 particle. Okay, if the two protons are and the N0 are at rest after the collision, find the initial speeds of the proton. Okay, so do you think you know what's going on here?
So the two of them are colliding, creating the second particle at the collision site.
Right. So does that tell you anything about how much energy or momentum they have to have before the collision?
They have to have enough so that it equals 0.
Sorta. I
Correct.
think you're saying the right answer, but I don't think the wording's correct, but I think you're understanding something. If you were to take the energy of one proton and add it to the energy of the other proton, can you tell me what that energy would be?
So that quickly,
Because remember, it goes from that energy to zero energy, except for rest energy, of course. They still have the rest energy of the protons.
we have to use the E equals, no, we can't use the gamma MC squared. So would it just be E equals MC squared?
Right, for the eta particle or whatever that Greek symbol is again. Basically, you had to have enough kinetic energy between the two protons such that when they lost all of it, that was enough to give the eta particle MC squared. So in other words, MC squared for the eta particle should be half of the energy of a proton, or half the kinetic energy of a proton. Does that make sense? You see what I'm saying there?
Yeah, so it would be 1/2 the kinetic energy.
One half the rest
proton for the
energy
proton.
of the eta is the energy of a single proton.
Okay. So we would have to find the rest energy for the eta.
Mm-hmm. I'm in the process of looking up what. Yeah, I was right. That's eta. Whew. I hate that one, and I hate xi, and I hate. There's a little squiggly guy, zeta. I hate zeta, eta, and xi. Those ones are always a pain in my butt. But yeah, so yeah, basically what's happening is the entire kinetic energy of one proton plus the entire kinetic energy of the other proton spontaneously added up to make the rest energy of the eta particle, and that's MC squared, where eta particle is 9.75 times 10 to the negative 28 kilograms times c squared. So that's really what you're looking at here. So E before is equal to gamma minus 1 m proton c squared plus gamma minus 1. They're the same. That's why I'm writing it twice. There's 2 protons.
Yeah.
Okay. Well, the E after, and this is actually kinetic energy before, I should just say that. And we're assuming basically sort of a completely inelastic collision. So the kinetic energy after is equal to 0, but the total energy before is gamma m, or and I'll just say 2 mpc squared, and the total energy after is equal to 2 gamma mp c squared plus m eta c squared. So you see, when you set these two equal to each other, you can see that, oh, excuse me, this is total energy. That's right. Oh, in this case, it's just that because there's no gamma anymore because none of them are moving.
Okay. MP C squared.
Yeah, so this and this are equal according to the conservation of energy. So I get 2 gamma MPC squared is equal to 2 MPC squared plus M eta C squared. And was it asking for the kinetic energy or the total energies of the protons beforehand?
It's asking for the initial speed of the protons.
Okay.
And there's the for it ask for the kinetic energy of each proton, and CS for the rest energy of.
Okay. Well, check this out. How I have it written. If I pull this over to this side, you see that you got a factor of 2 MPC squared common to both terms. So I'll say 2 MPC squared times this one's gamma, this one's minus 1. And then all I have left on this side is M eta C squared. So that's what I was telling you. All the kinetic energy of the protons went into creating the rest energy of the eta particle. So if it's asking you for the speed, all you have to do is calculate this, which is equal to that. So you already know that. And then all you have to do is say, okay, well, that's the 2 kinetic energies. So if you divide that by 2, you get the kinetic energy of one of them. But that kinetic energy is also gamma minus 1 times MPC squared. So you can then solve for gamma. It's a lot more steps than you might be thinking, but it's still fairly easy stuff.
So in order to find the speed, I have to solve the left side of that equation.
Well, no, you're actually, the left-hand side of the equation is twice the kinetic energy. So the right-hand side of the equation, if you take 1/2 of that, that's the kinetic energy of a single proton. So you just take the mass that they gave you, that's 9.75 times 10 to the negative 28, multiply that by C squared, and that'll be, and then divide that by 2, and that'll be the kinetic energy of one of the protons. But remember, kinetic energy is just gamma minus 1 times MC squared. So if you set that equal to 1/2 mass of the eta C squared, then you can solve for gamma. And of course, then you can use beta is equal to the square root of gamma squared minus 1 over gamma. So really, you're going to solve this for gamma, and then you'll be ready to roll. Do you see where that 1/2 came from?
Yeah, I'm still blanking where you get the speed. See,
Well, remember gamma has
so it's asking for the speed.
gamma
Uh,
is one minus one over
gotcha.
the square. Yeah, you got it now. Okay. I thought you were I thought
yeah, it's asking for gamma. Like, because it's asking for like the speed of like the percent speed in correlation to the speed of light.
you're right.
Gotcha. Oh, when I solved the MNC squared for the kinetic energy of each one and then divide by 2,
Mm-hmm.
I put in the answer and it said it was wrong. I got 4.39 times 10 to the negative 11th.
Okay, well, that's if that's the speed, then that would be way too nasty, right? That's like 4 times the speed of light. Is it asking for velocity in units of c? I mean, is that the unit that has a c?
I solved for the kinetic energy of each proton first. Or should I solve for the velocity first?
You can solve for the either one. The main thing is once you get that, you need the gamma, and once you get the gamma, then you can get the beta. I just got the gamma being this. So
Okay, I'll solve for gamma quickly.
I got like 0.633 for this times the speed of light for the velocity.
Okay, I got the 1.29 for the gamma.
You got something funky for gamma? You didn't get the 1.29.
I got that.
Okay.
So I got the same thing you did. And I got the same thing for beta.
Yep. That should be right. Now you did the kinetic energy first, so now you've got the answer to part B, right?
It said it was incorrect when I solved it.
Well, did you remember to divide by 2?
I
Right.
did.
Okay, so you took the MC squared of the beta particle, of the eta particle, and divided that by 2 and said that's the kinetic energy, right? And it looks like
Yeah,
MeV. So let's see, 9.75 e to the negative 28 times 3 e to the 8 squared. I divide that by 1.602 e to the negative 19 to put it in electron volts. That's 547 MeV. Now divide that by 2. I get
Wait, what was
274 MeV.
what was the 1.06 you said?
Okay, so what I did was I took that's conversion to electron volts instead of joules. 1.602.
That was the problem.
Okay, you were doing it in joules.
Times 10 to the. Okay.
Remember, the 10 to the 6 means mega, so that's why it's mega electron volts. Did we get a new person come in, or did we get Mary leaving?
They came in and left.
Okay, gotcha.
So in order to get mega, divided by 10 to the 6th, 210.
274. 270.
274.
I got 273.8764 times 10 to the 6th.
Hey,
Yeah, that's
Professor, I guess
correct.
I'm gonna head out, all right?
All right, no problem,
Thank you.
Colby. Do you have any questions before you split? No, guess not.
I think I had a calculation error where when I did, I got 207, so I gotta check quick.
Yeah,
So it was
9.75 times 10 to the negative 28 times 3 times 10 to the 8 squared. Then divide that by 1.602 times 10 to the negative 19th. That'll get an electron volts. And that'll give you 570 or 500 and something. I got 547.75 times 10 to the 6th electron volts. Then I divided that by 2 and I got 273.8764, which rounds to 274.
Why do you? So you did 4.3875 e to 11 divided by 1.062 e to the negative 19.
Yeah, I think what you said was right.
1.13 times 10 to the 8th. So I don't know where I'm going wrong with that.
I'm writing it out so you can see what I did, just to make sure we're on the same page and you didn't like just type in something errantly.
I think I typed in something wrong.
This gave me 87.75 times 10 to the negative 12th joules. Then I took that 87.75 times 10 to the negative 12th joules and divided it by 1.602 times 10 to the negative 19th joules per electron volt. And that gave me 547.753 times 10
Now it's working. I don't understand what happened.
EV.
I gotta figure out what happened now, because now that I plug it in again, it
Gave you the right answers?
is that what I did wrong? Yeah, that's probably what I did wrong. Hmm. Yeah, I divided by 2 earlier instead of I divided by 2 like too early,
Mm-hmm.
and I guess that messed up the calculation.
Yeah, that could do it because you might, by accident, you might actually come up with like twice or square root of 2, dividing by it twice or dividing by the square root of 2 or something weird like that can happen. So it's about time for my lab to end. So I guess that's about all I can fit in today. Hopefully that helps you. You got to learn those equations. You might want to just
Yeah.
have them all written down. One day in one of our lectures, I actually took the time to write down sort of all of them. The E, the gamma, the beta, the kinetic energy, the potential energy, the E squared is equal to P squared, C squared plus M squared C to the 4th, and the E is equal to gamma MC squared. L is equal to L0 over gamma, delta T is equal to gamma delta T0. All those things, just to have them on one sheet, and it might make it a lot easier for you to do this stuff. It's just because it's not really new physics other than the fact that the formulas are different. Does that
Okay.
make sense?
Yeah. Oh, thank you. I'll be heading out now.
Okay, see you, Jacob. Thanks for coming.